Here comes a very nice application of what we have learned about matrices and their eigenvalues and eigenvectors. It's called normal modes. You're very familiar with it. When you hit the string and you try to get a note on the guitar, you try to get it in a pure tone, which is a normal mode. So it's a pattern in which you have certain number of nodes or wavelengths along the string. And the dynamics is simply that nodal lines don't move, zeros don't move, and the amplitudes go up and down with the frequency of the note. So that's the simplest example. A more sophisticated example, which I've put as a figure at the start of this video, are chladni patterns, where you vibrate a plate and you put a little sand on it, and the sand moves from vibrating area to nodal lines, giving you the nodal pattern. What's the big deal about all this? When you have a many-body system, you have molecules, you have neural networks consisting of neurons. What rules is not behavior of individual particle, but the collective modes. And normal modes are very early, a very clean example of it. So the idea is quite simple and easiest to explain by thinking of a spring mattress or by thinking of a bunch of molecules interacting in some way or other. And on a classical level, there's a classical Hamiltonian of n particles. So this is kinetic energy term. And some potential that describes the potential energy of locating the n particles and molecules and whatever into n different positions. These particles interacting by van der Waals force, by electrostatic force, by whatever is correct formula for your particular physical problem. Now we assume that this potential has a minimum. So it's some minimal energy configuration in which nothing moves, typically an equilibrium configuration. You can think of a bunch of particles interacting by some forces, and you have a configuration that you can draw as a bottom of some potential in many dimensions. Maybe there are 3n such things. Now there's a particular choice of all of them, which we call x star, which has a property that when I draw this potential, it's minimal at that point. So that's a resting point of the system. All the forces just in balance and nothing moves. We assume that P of x is smooth. If we change a little bit the x, we find ourselves in a slightly different location, but not discontinuously different. So if you add a little perturbation to this, then you can think of the value at the minimum plus, and we just do multi-Taylor expansion, a second derivative plus a higher order term in delta x, which we will neglect. We'll just go the first two orders. Now, if we have an equilibrium, we are at the bottom of the well, so it's flat. And the first non-vanishing term is the matrix of second derivative. So let's define this to be a matrix, Bij, which is the value of the matrix evaluated equilibrium point. This is the curvature, And if I'm at bottom of the well, moving in any direction should increase energy, so they should have positive curvature. No matter how complicated, how rich the law of interactions of all these possible particles is, if I look to equilibrium and close to equilibrium, I always find that small deformations will be described by a symmetric matrix. But this ij goes over the degrees of freedom. For example, here there are n particles, each one of them having 3 coordinates. In the leading approximations of small deformations around static systems sitting at the bottom of its energy potential, we have an effective Hamiltonian which describes small deformations close to the bottom of the potential well. This is a parabolic approximation. State of the system, configuration coordinate times this transpose times this matrix. So all classical systems which abound can always describe in this way. So there's an effective spring, because this now looks like a harmonic oscillator, but in many dimensions, which has some kind of symmetric tensor stuck in here. 1/2 is just came from Taylor expansion, but basically because there are 2 terms here. Symmetric matrix can always be diagonalized. There is some orthogonal transformation. This is a real matrix, which I will not write out, but the result of it, if I go into new coordinates, matrix orthogonal transformation, and more generally unitary, these are complex fields, where these factors are obtained by diagonalization. And they're called normal modes. You can rewrite this process in new coordinates. The symmetric matrix basically defines some kind of ellipsoid which has major and minor and semi-minor axes. Because it's symmetric, it has orthogonal axes. And when you go to those axes, you just get a sum of harmonic oscillators. Each one of them has its velocity, and it has its displacement, which is now what we have already derived before called an eigenvector. And the number in here can be interpreted as frequency. This is totally general for any classical Hamiltonian that's smooth around its bottom. It can be generalized to Hamiltonians which have critical points which are maybe top of the potential. You can have solutions which are unstable in all directions, or saddle point, something that has 0 derivative, but in one direction you climb, in potential direction you go down, in which case it's called a hyperbolic mode. And instead of having sines and cosines describing a time evolution, they'll have hyperbolic sines and cosines along the eigen directions of the system. Totally general setting. Next, we'll work out a few examples.